we are looking for a prime number x such that it satisfies this particular equation. Now let's talk about the sum of the divisors. This sigma stands for the sum of the divisors. And let's talk about a slightly more general way to determine sigma of a prime power. We're just looking for a prime number, but let's look at the prime power, let's say 5 cubed. Okay, 5 cubed. Okay, so this literally means to sum up all of the divisors of the number 5 cubed. You don't even have to know that's equal to 125 to do this, but you do know, because of the uniqueness of the prime factorization, that those divisors are 1. One is a divisor of any integer. 5 to the first power, and I'll just put that for emphasis, is also a divisor of 5 cubed. 5 squared and 5 cubed. A number is a divisor of itself. Okay. Now I'm not even going to go to the trouble to add this up right now. We're going to write down a result that I'm not going to prove, but it's fairly easy. This is an example of a finite geometric series. It has a very well-known sum in a closed form that's not too hard to prove. That would be another video. But you can. This is actually equal to 5 to the 4th. Notice how we increment this 3. This is 5 to the 4th minus 1 over 5 minus 1. You know, 5 without an exponent, well, it's 1, but it's usually left out. Now, let's see what this does for us. This would be let's see here, that's 625. This is 624 over 4. And that's easy enough to do in your head. That's 156, right? 156. 4 times 156 is 624. Okay, now if you take the time to add these up, this is 125. Plus 25 is 50. Plus another 5 is 155, 156. So you see, there you go. There's your closed form. And notice how we incremented. This 4 right here is 3 plus 1. Now this is going to come in handy, because this function here is what they call multiplicative. You can split it apart. And that's, again, I won't prove that. It's not a hard proof. It appears in almost every number theory book I've seen. But so here's our original problem. Now, so we write it as phi of 3 squared because 117 is equal to 9 times 13. Okay. And you see, we wrote 9 as 3 squared here. Now again, I didn't prove any of this, but it's not hard to believe that this thing splits. So we split it up into 3 separate sigma functions. 3 squared is one of the factors here. 13 is one of the factors. And x, which is, remember, is a prime. X is a prime. So we've already seen how to do sigma of a prime power, right? Even. So the prime or a prime power. So let's see what this does for us, okay? So again, y'all, just trusting this result right here, this would be 3 cubed minus 1 over 3 minus 1, which is 2, right, folks? Now, for 13, we would have 13. This is 13 to the first power, right? So we would have 13 squared minus 1 over 13 minus 1, which is just 12, right? So, yeah, this is just 12 right here. Okay, now here we do know that x is a prime, and it's x to the first power, right? That was given. And so this would be x squared minus 1 over x minus 1. See, folks, again, maybe you're not used to seeing x as a prime, but it is specified that x is a prime. And so you're just using this result here with the exponent equal to 1. Okay, so there we go. Now, what happens with all of this? Well, let's see. This is equal to, let's see if I can write this down, y'all. Let's see if we can do this math. This would be 27 minus 1 is 26 over 2, so that would be 13. Okay. Now, what is this number? Okay, getting a little big here. This is 169 minus 1, which is 168 divided by 12, y'all, and that is 14. Okay. Now, remember, x squared is equal to x plus 1 times x minus 1. So this would just all be x plus 1, right? Isn't that cool, folks? Remember, yeah, this is x plus 1. Remember, this part here is x plus 1 times x minus 1. So the minus 1 factor would cancel. Okay, now remember, what was all this supposed to be equal to? This is equal to 1456, okay? Where it's this 1456, right, is what we're doing here. It's equal to 1456. So what we get is 1456 is equal to 13 times 14 times the binomial factor x plus 1. Y'all, I love prime numbers. How can you, did you notice that? But y'all, it turns out this is equal to, and you can do this pretty easily. It's kind of an intermediate algebra exercise a lot of times, but this is equal to 2 to the 4th power. It's not hard to believe there's a lot of powers of 2 in this 4-digit even number. And then guess what appears in the factorization? 7 times 13. Okay, now again, y'all, that takes a little bit of work to do that. I don't want to waste time on the video doing that. But so you see what happens here. This works out rather nicely because what we get right here, 14 is 2 times 7, right? So you see, if you look at this carefully and look at the cancellations that would occur, one of these 2's will cancel with one of these 2's, leaving 3, and the 7 and the 13 will cancel out, right? So you end up with 2 cubed. And I love this. 2 cubed is equal to x plus 1. Without really lifting a finger other than the effort required to find this prime factorization. And so what you get is x equals 7. And x certainly is a prime number, folks. So anyway, I thought that was fairly cool. Hope you liked it. Let me know what you thought. I like these kind of problems that deal with the number theoretic functions. And so let's come back up here and call it x equals 7. And let's call it a day.